This video is not really about any new concepts. It's just an application of equilibrium constants to solving some equilibrium problems. So this is just kind of a techniques and tricks for problem solving, and that's all we're doing in this video. So there'll be a lot of example problems to work out. I've categorized the kinds of equilibrium calculations that you're most likely to have to do into three cases. Case one, the type 1 sort of calculations, are when you know the equilibrium concentrations or the partial pressures at equilibrium. And what your objective is you want to find Kc or Kp. These are the easiest kind of problems to do because all you have to do is just substitute the known values of concentration or pressure, whatever you're given, into the expression for K. So for example, if we have this reaction at equilibrium and we know that the concentration of N2 and O2 and NO are what are given here, and our job is to find the value of Kc, well, here's what Kc would be. It would be concentration of NO squared divided by concentration of N2 times concentration of O2. So we'll just plug in the values that we were given. So for NO, that's 4.7 times 10 to the negative 4th molar. That's going to be squared. For N2, it's going to be 0.042 molar. And for O2, 0.0078 molar. Calculate this all out and you get 6.7 times 10 to the negative 4th. Pretty easy. The second case is a little more difficult. These are problems where we know the initial concentrations or the partial pressures, and we know one equilibrium concentration or partial pressure, and our objective is to find out what is the equilibrium constant. So here's the strategy. We're going to use a thing called a Rice chart. And I'll explain what that is as we do our first example problem. And this will help guide our stoichiometry. It's kind of like a BCA chart, which we've used in the past, except for there's no after because we don't come to a definite stopping point. We just come to an equilibrium. And then we're going to use the K expression to guide which of the values that we got from this Rice chart we're going to need to ultimately solve our problem. So here's the problem that we want to solve. 12 moles of SO3 are put in a sealed flask. It's a 3-liter flask. We have the reaction here. And then at equilibrium, we know that 3 moles of SO2 are present in this 3-liter flask. And our question is, what's Kc? Let's go to a good working space where we have a little more room to work and solve this problem. So first of all, let me introduce you to the concept of a Rice chart. The Rice chart has rows that correspond to those letters in Rice. The first one is the reaction. And in this row of this chart, we're going to put the reaction. In our case, it's 2SO3 in equilibrium with 2SO2 plus O2. So that line is the reaction line. I'm leaving off some details here. Everything's gaseous, so I don't have to worry about that. It's a homogeneous reaction, and I don't have to think about what's going to have values in my K expression or not. Okay, the next line is I, and that stands for initial. So these are the starting conditions. And these are going to be in moles per liter or atmospheres, depending on what you have. We're trying to find Kc, so we want this in moles per liter. We have 12 moles of SO3, and it's in a 3-liter flask. 12 divided by 3 is 4, so that's 4.0 molar. And that's the only thing that's in the flask. So initially, there is 0 concentration of both SO2 and O2. The next line is C, which stands for change. Here we're just laying out the stoichiometry. So SO3 has a 2 in front of it, and it's a reactant, so we're going to lose it. We don't know how far the reaction is going to go before it reaches equilibrium. So what we're going to do is we're going to say it's going to lose 2x moles. Now the 2 comes from the coefficient. The x just means we're not really sure how far this is going to go, so that's kind of a stand-in. But we know that if we lose 2x moles per liter of SO3 because of the 2 to 2 ratio, we are going to gain 2x moles of SO2. And because of the 2 to 1 ratio, we are going to gain x moles per liter of O2. Then the E stands for equilibrium. So here we're putting down what are the equilibrium concentrations. So we started out with 4. Our change was we lost 2x, and so 4 minus 2x is our equilibrium concentration of SO3. We started with 0 and added 2x. So 2x is our equilibrium concentration of SO2. And going from 0, added x. X is our equilibrium concentration of O2. So now, we want to find Kc. Kc is going to be concentration of SO2 squared times concentration of O2 divided by the concentration of SO3 squared. Now in terms of our chart, SO2 concentration is 2x, and we're squaring that. O2 concentration is x, and SO3 concentration is 4.0 minus 2x, and we're squaring that. So we can simplify a little bit. Kc is 4x cubed, and on the bottom we have still 4.0 minus 2x quantity squared. Okay, what do we know here that we can use to get rid of the x and find out what Kc is? Well, here's one thing that we know. We know that there are 3.0 moles of SO2 in our 3-liter flask at equilibrium. So that means that 2x is equal to 1 mole per liter. So that means x is equal to 0.5 moles per liter. So that means that Kc is equal to 4 times 0.5 cubed over 4.0 minus 2 times 0.5, with that quantity being squared. Do all your calculations and you come out with 0.056 as our value for Kc. Here's another example. Pure ASH3 is put in an empty, rigid, sealed container, and the pressure is 392.0 torrs. After 48 hours of decomposing, here's the reaction that's given. The total pressure in the container is constant at 488 torrs. What's the equilibrium pressure of H2 is the first question we have to answer, and then what is the value of Kp? So first let's set up our Rice chart. The reaction, 2ASH3, gaseous, is in equilibrium with 2AS, which is a solid, and that's important to know because it's not going to be in our equilibrium expression, plus 3H2 gas. Initial, we have 392 torrs pressure of ASH3. This solid doesn't exert any pressure. We don't have any hydrogen until the reaction starts happening. Here's our change. We're going to lose 2x, we're going to gain 2x, and we're going to gain 3x in our pressures for those three. But remember, that really doesn't exert a pressure. At equilibrium, this will be 392.0 minus 2x. This will not exert a pressure, and this will be 0 plus 3x, which is just 3x. So what's our pressure of H2? Well, the total pressure is 488 torrs. And that's equal to the pressure of ASH3 at equilibrium, which is 392.0 minus 2x, plus the pressure of hydrogen, which is 3x. We're just summing those partial pressures up according to Dalton's law of partial pressures. So if we solve this for x, which is just simple algebra, you end up with 96.0 torrs. So that's the pressure of H2 at equilibrium. Now we want to know what's the value of Kp. Well, Kp for this reaction is going to be the pressure of H2 cubed divided by the pressure of ASH3 squared. In terms of our chart, that's 3x cubed over 392.0 minus 2 times x. So Kp, with some numbers in here, is 3 times 96.0, that quantity cubed, divided by 392.0 minus 2 times 96.0, and that quantity is squared. Forgot to square it up here. Work at all the arithmetic. This comes out to 597. The next case is the most complicated. This is when we know the initial concentrations or partial pressures, and we know Kc or Kp, But what we need to find is what are the concentrations or the partial pressures when we reach equilibrium. So here's the strategy. We're going to use a Rice chart again to guide our stoichiometry. And then we have to use the K expression to figure out what values we need from the chart. Here's an example of this kind of a problem. We have a K value that's given. We know the reaction, and they tell us how much of the two reactants are added to the flask. Looks like there's no product initially, and they're allowed to react. And we have to find the equilibrium concentrations of all the species. We're going to switch to a workspace, and then we're going to do 4 problems in a row just to do a lot of practice with this kind of calculation, because it's a little bit complicated, and it's also very important for a lot of the things we're going to be doing for the rest of the course. Let's start this problem out by setting up our Rice chart. Here's our reaction. H2O is reacting with Cl2O in equilibrium with 2HOCl. Everything's a gas. Initially, what's our concentration of H2O? Well, we only have a mass, so we're going to have to change that into moles. It's in a 1 liter flask, so however many moles we are, that's the concentration. So we'll take 1.0 grams of H2O. The molar mass of H2O is 18.015 grams per mole. And this is going to leave us with 0.056 moles. So in the 1 liter, that gives us a 0.056 moles per liter concentration. We have 2 grams of Cl2O. The molar mass is 86.905 grams per mole, and this gives us 0.023 moles. So in 1 liter, 0.023 molar is the concentration, and we don't have any HOCl at first. The change line, minus x plus 2x from the stoichiometry of the equation. So at equilibrium, this will be 0.056 minus x. This will be 0.023 minus x. And this will be 2x. What's Kc? That's what we're trying to find here. It's concentration of HOCl squared divided by concentration of water times concentration of Cl2O. In terms of our chart, first of all, Kc is 0.90, they tell us. 0.090. And that's equal to, well, at equilibrium, concentration of HOCl is 2x. That's squared. Concentration of water is 0.056 minus x. The concentration of Cl2O is 0.023 minus x. So now we have a quadratic equation. Now, you guys all know how to solve these things. I'm not going to go through all the details here. You might solve this by graphing. You might solve it by using a solver on your graphing calculator. You can solve it by guess and check. You can use the quadratic formula. There's all kinds of different strategies, but when you do it, you find out that x is equal to 0.0046. So what does that mean? Well, we wanted to know all the concentrations. So concentration of HOCl was 2 times that. So that's 2 times 0.0046. And so that's 0.0092 molar. The concentration of H2O at equilibrium, well, that's going to be 0.056 minus 0.0046. And that comes out to 0.051 molar. And then the concentration of Cl2O, that was 0.023 minus 0.0046. And that ends up being 0.018 molar. You know, so we had to solve a quadratic there. That is quite often the case. So whatever is your favorite method for doing that, you should get yourself used to doing that a few times. Here's another one. A mole of HOCl is added to an empty 2-liter flask and it's allowed to react. What are the equilibrium concentrations of all species? This is the same reaction that we had, except it's going to happen in reverse. So let's set up our Rice chart by flipping this around. So 2HOCl will be in equilibrium with H2O and Cl2O. What's our initials? Well, we have 1 mole in a 2-liter flask, so that's a half a mole per liter. And we don't have any water, we don't have any Cl2O. Change, minus 2x plus x plus x. So at equilibrium, this will be 0.50 minus 2x. This will be x, and so will this. What's Kc? Well, the number will be the reciprocal of 0.090 because we reversed the reaction, and that ends up being 11.1. And the expression for Kc is concentration of H2O times concentration of Cl2O, because those are our products now, divided by concentration of HOCl squared. So in terms of our chart, we know that Kc is 11.1 now. And we know that the concentration of H2O is x, and so is the concentration of Cl2O, so that's going to be x squared in the numerator. And then 0.050 minus 2x squared will be in the denominator. This one's a little bit simpler to solve. We could take the square root of both sides, and then it's a kind of a simple algebra problem. But when you solve it, however you do that, you find out that x is 0.22. So we needed to know all the equilibrium concentrations. So concentration of H2O is going to be the same as the concentration of Cl2O. That's just going to be x, and that's 0.22 molar. The concentration of HOCl, well, that's going to be 0.50 minus 2 times whatever x was, which was 0.22, we found out. And this works out to 0.065 moles per liter. Here's another one. We're given Kp. We have the reaction here. N2 is added to an empty flask until the pressure is 0.8 atmospheres, and then oxygen is added till the total pressure is 1 atmosphere. What's the equilibrium pressure of NO? Set up the Rice chart first. So N2, a gas, reacting with O2, also a gas, in equilibrium with 2NO, which is also a gas. Initial. Well, our pressure of N2 was 0.80. And then once we added the oxygen, the total pressure was 1 atmosphere. And by Dalton's law of partial pressures, that means that the O2 would have to be the rest of that pressure, which would be 0.2 atmospheres. Reaction hasn't happened. We didn't put any NO in there, so that's a 0. The change is going to be a minus x, and a plus 2x. At equilibrium, this will be 0.80 minus x, this will be 0.20 minus x, and this will be 2x. Kp is going to be equal to the pressure of NO squared divided by the pressure of N2 times the pressure of O2. In terms of our chart, that means 0.050, that's Kp, is equal to, the pressure of NO is 2x, so that's going to be squared. Pressure of N2 is going to be 0.80 minus x, and the pressure of O2 is going to be 0.20 minus x. So now we got a quadratic to solve. Use your favorite method. My favorite method told me this is 0.039 for x. So that means the pressure of NO at equilibrium, which was 2x, equals 2 times 0.039, and that comes out to 0.078. And we put atmospheres in, so we get atmospheres back out. One more. 2 moles of CO2 is put in a 5-liter container, and here's the reaction it's given to us, and here's the Kc, so it's concentrations that we're interested in. What's the equilibrium concentrations of all species at the end? Let's set up our Rice chart. 2 CO2, it's a gas, in equilibrium with 2 CO, also a gas, and O2. Initial. Well, we had 2 moles of CO2 in a 5-liter container. 2 divided by 5 is 0.4, so that's a 0.40 molar concentration. And that's the only thing we put in there, so those are both zeros. That's the start. Change, minus 2x plus 2x plus x, coming from the stoichiometry of the reaction. At equilibrium, this will be 0.40 minus 2x, this will be 2x, and this will be x. So what's Kc? It's concentration of CO squared times concentration of O2 divided by the concentration of CO2, which is also squared. In terms of our chart, well, Kc we know is 2.0 times 10 to the negative sixth, and concentration of CO is 2x. That's going to be squared. Concentration of O2 is x. And then in the denominator we have 0.40 minus 2x, but that's also going to be squared. Now here's where we can do a little trick that often works. We notice that the K value that we have here is very small, much smaller than 1. So what that means is that 2x is going to be very, very small compared with 4, because there's not going to be very much of a change. As this reaction reaches equilibrium, we're going to have not very much product. We're still going to have mostly reactant. So compared with 0.4, that 2x is probably going to be ignorably small. So we can make this simplification. We can say 2 times 10 to the minus 6 is going to be pretty much equal to 2x squared times x divided by 0.40 squared. And just ignore that 2x because it's going to be very small compared with 0.4. How do you know if you can do this or not? Well, you can always just try it out, and then we have a little bit of a test that we can do at the end. This simplifies to 4x cubed over 0.40 squared. So now this becomes a pretty simple problem to solve. We can just multiply both sides by 0.40 squared, divide by 4, take the cube root, and find out what x is. X is equal to, when we do that, 0.0043. Now here's the test. If you weren't sure you could make that simplifying assumption, you can take this number, 0.0043, and divide it by 0.40, and it's 0.011 approximately, which as a percentage is 1.1%. So we have this rule called the 5% rule. If that x turned out to be less than 5% of what your starting concentration was, when you take significant figures into account, you were perfectly fine leaving out that 2x quantity because it wasn't going to make any difference anyway. And it just made your math simpler. Okay, now that we know that, we can solve our ultimate problem here. The concentration of CO2 is going to be 0.40 minus 2 times our x value that we got, and that ends up being 0.39 molar. So you can see it didn't change very much. It only went down 1/100th. So the assumption was fine. Concentration of carbon monoxide was 2 times x, which is 0.0086 molar, and the concentration of oxygen was just x, so that is 0.0043 molar. Those are all the kind of cases that you're going to find, and just applying that rice chart and just thinking your way through what concentrations and pressures have in common with each other and with the Kc value can help you really solve these problems effectively.